All the aspects of the computational exercise, I didn't explain them very clearly. So when we do that towards the afternoon period, I'll go through it a little more carefully. Okay. And so what I'll do is I'll make sure I walk around and then so we'll actually slow that down a bit. So this morning, what I'm going to do is I've sent a new set of slides. Well, it's not new; it's just augmented with a little more material. And what I'm going to do this morning is I'm going to slow down and put stuff on the board so that everybody's on the same page regarding how we transition from the game-theoretic model to the variational problem, and then how do we kind of get to the existence and uniqueness statement. So what is the roadmap that we're looking at? So and I think this will be useful. So that from the standpoint of developing a broader picture of what we're trying to convey here. Okay. So let's just start with that. And I'm gonna try and retain this for the rest of the day. So at the heart of it, we have okay. This is an x1. Okay, so this represents the Nash game, which I'm going to denote by theta, where theta represents the collection of objectives, and x. Actually, I'll flip the direction. X and theta. Right? So this is the Nash game that is the focus of this class. Okay? Now, what did we do when we had convexity and so actually we just need convexity of theta I. You also need differentiability, but even without differentiability you can write out a variational inequality. Okay? So from here we showed that this is equivalent to this problem. Vi xf, where f is and capital X is the Cartesian product. Okay. So yeah, and the reason why I do if and only if is because if I get a solution of the variational inequality problem, I have an equilibrium of the game. So I lose nothing. Now there are some settings where you end up losing equilibria, right? So, but in this case, no, right? Every equilibrium is captured by a solution of the variational problem, and every solution of the variational problem can be constructed as an equilibrium. Okay, now under some conditions, what we show is this. Okay, I don't want to put the arrow there. I'll just put it up here. Now, if you look at Vi xf, this problem, under some conditions, it's equivalent to some other problem, minimize f of x, x and x. And this is when under the observation of integrability. And I'm going to explain to you what I mean by this, okay, right now. So this is an optimization problem. Why is this important? The reason why this is important is because this problem allows us to say a lot more, because for a variety of reasons. First of all, there's a natural objective that you're trying to minimize. As a consequence, we have a lot more in terms of creating bounds, a variety of things. And you'll see that. But before I make that step, I want to just tell you something about integrability and give you some examples of when it shows up, okay? I'll just use this board because we're not using the screen right now. So suppose I'll just pull this out. So if I gave you a problem like this, let's take a simple problem so that we understand what an integrable game is. So suppose I gave you a problem like this, half x1 squared plus x1 x2, and I want to minimize this in x1. Okay, and I'm going to make it unconstrained for the time being. So let's not worry about the constrained aspect. Okay, and I'm minimizing this in x2. It's a simple game where I just have two players, right? So the first thing you want to check if you want to use this is convexity. So the question is this function convex in x, right? So step one, check for convexity. In player payoffs, in player costs, right? If you look at this one, what you notice is if you take the second derivative of theta 1 in x1 squared, what you end up with is 1. Okay, so it's a convex function. Okay, is everybody with me? Similarly, okay. Now if you write down, so what is our usual approach? This is equivalent to Vi, in this case it's Rn. So I want to make sure, does everybody understand why the set in the Vi is Rn? Or actually it just should be R1. Because your x1 can lie on the real line, right? There's no requirement for that it be constrained. Okay, so once I have that, I just need to write the gradient of this. The gradient of this is x1 plus x2. Okay. Similarly, this is R1 2x2 plus x1. Is everybody with me? Okay. Next. So now I've got the Vi. So now this remember what we did yesterday. This is equivalent to a single Vi in R2, 2 dimensions, with this mapping. You just take each of the gradient maps. Okay, and this is f of x. Is it Emily? I forgot your name. What's your name? Emily? Is that clear? Is there something that I've missed? Just want to make sure. Because the reason I wanted to do this example today is so that we're all on the same page. If there's yes, please.
Is there just something written next to the 1/2 in the second?
It's minimize in x1.
The one below after the 1/2.
Oh, sorry. What did I do? I put. What did I put? I put 4x squared. So it was basically 2x2. No, but it's not right? Because this is 2x2. So we'll just make it x2 squared. Sorry. Sorry about that. Anything else? Asim? Claire? Christy?
It just does a sleep
No, no, no. Please.
Why is the first VI R1 and the next one R2?
So this is because here you're optimizing. This is a consequence of an optimization problem in one dimension. This is in one dimension. That's why both of these are R1. Now there are two VIs. You can write them as a single VI. That's not always the case. In this case, you can. Remember, I told you about this relationship between Cartesian VIs and a single VI, right? So it turns out you can write this as a single VI in two dimensions, and that's why I have an R2 here. And then you're using the mapping, which is the concatenated gradient map of these two. Clear, Fabio? Clear? Okay. Okay, so now this is an important step, right? So at this point, what I'm going to do is I'm going to observe that this mapping, let me just write it. So this is, I'm just going to call this f of f, where f of x is defined as okay. So what you notice from here is f of x can be viewed as the gradient of some other function f of x, little f of x, right? Why is that? Before that, let me do something so it makes it obvious. If you take the Jacobian, so the term Jacobian is reserved generally for vector mappings. If you take the Jacobian, you take each element and differentiate it by all the variables. You differentiate this in x1, you get 1. Differentiate this in x2, you get 1. In x1, you get 1. In x2, you get 2. So what you get is a symmetric matrix. Okay? So whenever you take the Jacobian of the mapping and you get a symmetric matrix, your first thought should be, well, this mapping is actually the gradient of some optimization problem. Because what functions have symmetric Hessians? So basically just standard scalar functions. Right? So then you say, oh, so I can write this, so I know this is really the Hessian of some function. It's the Hessian of some function, right? And this step, this is equivalent to integrability. Not always true, but when it is true, it's very useful. So we say that the game is integrable. Okay, or in fact, you can often say the VI is integrable because it's equivalent to another optimization problem.
Sorry, but this is not the case of G and E we talked, right?
No. So this is just pure V. Yeah.
And
so we have to be a little careful. So there are settings, and I'll show you some other variations where you don't get a pure game, but what you get is a constraint problem whose KKT point is exactly, and then in the GNE, in the shared constraint, it's true. Like I did it yesterday, remember?
Yeah. And the condition for integrability is just symmetry or also being positive semi-definite?
Oh, so the first thing is, so that's a good question. From the standpoint of equivalence, all you need is symmetry. The only issue is that what is the VI corresponding to a non-convex optimization problem? If I gave you an optimization problem that was not convex, then the variation inequality represents a stationary point. Okay. So if you give me the VI, and the VI happens to be the stationary point of some non-convex problem, you're still okay. Right? I could just get a stationary point, because getting stationary points is easier. Right? Now, if you want to make sure all of these equilibria are captured, then you need positive semi-definiteness. Okay, so Jalal makes a good point. I want to make sure. So I want to distinguish the need for positive semi-definiteness. But the first thing you notice is, if this is the Hessian, what can you do with it? Right? What can you do with this? So what happens is, if you look at this problem, you look at this problem, what you can say is that essentially f of x is equal to the gradient of f of x. Okay? And how does that help you? The reason it helps you is, remember our variational inequality problem was y minus x transpose f of x. Well, now you're left, you just change this with the gradient. But what is this? This is the stationarity condition of an optimization problem. It's necessary and sufficient if it's convex. Otherwise, it's only necessary. So this is the necessary condition of minimize f of x, x and x. But we're always interested in necessity and sufficiency because I want to make sure that if I work with this problem, I get exactly an equilibrium with this game. So these arrows have to be bidirectional. Okay? So now the question is, where did I get this from? Does everybody know where I got this from? Just from the definition, it was f of x, and now we know f of x, I observed it to be the gradient of some function. Okay? And so as a consequence, I could see it's equivalent to some and this is under the Hessian, the Jacobian of this being positive semi-definite.
So can we say that, sorry for interrupting, so if Jacobian matrix, if it's symmetric,
Yeah.
of course we have equivalent optimization. And
Yeah.
if it's positive semi-definite, we can say it's equivalent optimization.
No, let's be
Convex.
no. Let's so if it's symmetric, right? If it's symmetric, then what happens is that you have an optimization problem. But the issue is for you to go now. You have to be a little careful. So if you got a stationary point of this, you get a variational. So you get you get this vi, which is then equivalent to an equilibrium. Now, what happens is that if you have so it's only one directional, and if you want to make sure it's bidirectional, then you need convexity. So in your problem yesterday that you pointed out, you had a but your problem was a little different. So in your problem, what you did was you actually brought in the Lagrange multipliers and you constructed another problem. So look how this problem is. This problem is only taking the gradients to begin with. So I think when you have bilinear terms, so we have to be a little careful about some of those things. But here, all that you're doing is you're just sticking with the objectives. You're starting with the objectives of the players, writing it as a VI, writing it as a larger VI, observing that the Jacobian is symmetric, and then saying that, oh, if it's symmetric, it's integrable. Right? Now, once you have this, so why is this useful? This is useful because under integrability, I can do lots of things here. I can talk about uniqueness, existence, and so on. Okay, a bunch of things. Okay, now when I don't have integrability, no integrability, so if it's no integrability, then how do we show existence? So the way we showed existence yesterday was we came up with sufficient conditions for solutions to the VI. Right? So let's remind ourselves of some conditions. F is continuous. And X is closed, convex, non-empty, compact. This is one condition. Here's a second condition. So, if I can check that, okay, there exists some vector x ref in X such that the lim inf so this is some condition. It's often referred to as the coercivity condition. If this is often called coercivity. So here what do I need? I need this plus f continuous plus x closed convex non-empty. Is that clear? So two avenues. One is if we were able to magically observe that the VI was the represented the necessary and sufficient conditions of optimality of an optimization problem, then you can immediately look at the optimization problem, turn your attention to it, and make statements about it. Those statements include the existence of a solution, the uniqueness of solution. All of those statements come from optimization theory. For instance, uniqueness follows if the problem is strictly convex. Existence follows if the function is coercive over the set. Now, if you don't have integrability, then you need to leverage the properties of the mapping F and the properties of the underlying set X. So if F is continuous, X is closed, convex, non-empty, compact, you get existence. What about uniqueness? So for uniqueness, there are two avenues. One avenue is F is a strictly monotone map. On X. Second, F is a P map, and I'll define that later today, on X, assuming that X is can be written in this form. So this is just that it can be expressed as the Cartesian product of a bunch of sets. Okay, so this is uniqueness. Okay, so let's make sure that everybody's on the same page now. Okay, so this is like a roadmap that allows you to go from optimization, from convex Nash games. Right? Why they're convex? Because each player's objective is convex. Is there a light on this side?
Yeah, I can turn it on.
Okay, so let's make sure that everybody is with me here. Are there aspects of this that you're not seeing? Anna, is that clear? Is this part clear? Yeah.
I have a question.
Yeah.
You mentioned about the bidirectionality being of this equivalence being true only for when F is positive semi-definite. But when you say unidirectional, which direction is the one that we can do?
Yeah, so that's a good point. So, for instance, if it turns out that this is symmetric, then you just need it to go in this direction. You actually have the right direction. The problem becomes if you've gone in this direction. So now so yes, I stand by that. If you have, because you can have non-convex functions whose stationary points are variational inequality, and they are. So for instance, an example of that is just this problem, right? So if I just gave you this problem, so Anubhav's question is, suppose the optimization problem is non-convex that leads to this. Let's take a simple case. Suppose I take half x1 squared plus 3x1 x2 plus 2x2 squared, right? Now this is an x1 x2, so the gradient of this function is x1 plus 3x2 and 3x1 plus 4x2. The Hessian of this is 1, 3, 3, 4. Now you can see this is not positive definite, right? But now if you look at this VI, I can write this. If you look at this, these represent the gradients for this problem, right? So you can write it as minimize, it should be x1 squared over 2 plus 3x1 x2 minimize 2x2 squared plus 2x2 squared plus 3x1 x2, right? Now, look, an equilibrium of this game. Now you might say, that's weird. You had a non-convex problem, but now you have a convex Nash game, right? So what has happened? Can someone tell me what has happened?
But they are equivalent, right?
Yeah, they're equivalent, but it seems like this should be easy, right? Is it? What is it about this problem?
That the optimization problem contains a solution to this equilibrium problem, but also many other solutions that may not correspond to equilibrium.
So one thing that you notice is that so you're right. So if you look at this problem, but from the standpoint of this, if you wanted to optimize this problem, if you want to compute an equilibrium to this game, from that standpoint, how easy is it still? So if I tell you that if I get an equilibrium of this game, what is that equilibrium? It's convex, as I told you, which means it's equivalent to Vi x the gradient, right? Now you might say, oh, it's equivalent to this Vi. How easy is this Vi to solve directly? Okay, and it turns out, here's the interesting thing. If you try and solve this Vi directly, it's a little nasty because this mapping now is no longer monotone. Okay, but here's the interesting thing. The thing is that if you look at the optimization problem, if you want to get an equilibrium of this, any equilibrium of this satisfies this. And here, what is interesting is you don't need a global minimum. So the point I made about global minima, you have to be a little careful with what you're trying to optimize. In this particular case, if I get a stationary point, because the variational inequality by definition is variational, it manages local properties. You just need to get a stationary point of this, because a stationary point of this satisfies this variational, right? So now that's true if the set is convex. The set itself is non-convex, then you're dead in the water. Can't do anything, right? But here the set is convex, so I get a stationary point of this, and that's an equilibrium of this. Okay, so from that standpoint, it's better if you have this integrable structure to just get a stationary point of that problem, because getting a solution of this Vi is harder because the mapping is in monotone. Okay.
But it seems that we have a Nash game with not unique solution, multiple solutions, because it's not positive semi-definite.
Yeah.
And those solutions are stationary solutions of the
Yeah.
optimization problem.
Yeah. And so you get any stationary point, it's a solution to, it's an equilibrium of this game. Now you can't say anything more. The reason is that this problem is non-convex. Okay, but at least you know you can compute it. Okay, so integrability helps even from a computational standpoint. Yes.
Silly question.
No, nothing. Sorry.
Came up from the global, the first formulation of the optimization problem for any player. How do you?
So, how did I do that? I just observed it. So you can look at this, and the first thing you have to see is, look, if you started with this optimization problem, you notice that it's because it's an optimization problem, the Hessian is obviously symmetric, But when you look at it, what you notice is that you can construct a game whose Jacobian, so I guess I didn't do that. I said, oh, let's make sure that f of x is exactly this. But if f of x is exactly this, it can be viewed as this itself is going to be theta 1. And it turns out that you can look and see, oh, the theta 1 should be this and the theta 2 should be that. Okay? So does everybody get an understanding of the roadmap here? We have a Nash game. The Nash game has convex strategy sets and convex, not payoff function, cost functions. In that case, you can show an equivalence between an equilibria and a solution to the VI. When you have integrability, which means the Jacobian of the mapping is symmetric, then you have that problem can be recast as an optimization problem. That observation is very useful because then we can leverage a rich theory of optimization in terms of establishing existence, uniqueness, and computing equilibrium. But in a lot of settings, that's not true. And as a consequence, existence requires directly looking at the mapping and the set. That's what this does. Uniqueness requires looking at the mapping and, of course, the set. And computation I haven't talked about yet. We'll have to leverage properties that go well beyond optimization. Okay. So when you have integrability, the problem is in some sense, what you should think about is that the interactions across players are almost symmetric. So look at this interaction and look at this interaction. Right? Now if I just give you a game and I say, oh, look, these interactions are symmetric, then clearly you're going to get symmetric Jacobians. Is that true in general for games? Not really. But you have a well-structured game where that happens, and when that happens, you need to take advantage of it. Okay, but there are games where it doesn't, and we make no value judgment about them, right? Questions? Yes, Jalan? Yeah, Ashwini? Priyanka. I'm sorry, I keep calling you Ashwini. I don't know why. I apologize. Yeah, go on, Priyanka.
We can rename it. The second point, it's not very clear what you mean by L is P-map.
Yeah, I haven't defined it. So let me briefly tell, I'll do it later. It's another condition under which I get uniqueness.
Could you give us one example of parallel where we end up with a non-integrability?
Yeah. So for instance, if I had, so as I make this 4, if I make this 4, so non-integrable game. So if I have minimize x1 squared over 2 plus so the gradient map is Is that clear? Is not equal to its to its transpose. Okay, so not non-integrable. Jalal, you had a question?
What you didn't mention is, okay, how to explore uniqueness existence if it's integrable, if you have optimization.
Yeah, so the way to do that is we leverage optimization theory. And the way to leverage optimization theory, so that's a good point. Okay. So, existence under integrability. So this so basically it suffices to focus on this problem. Okay. So case 1, X is compact, F is continuous. It implies, so there's a theorem in analysis called Weierstrass's theorem. So Weierstrass's theorem says so I don't want to give you the whole theorem, but basically what it says is a continuous function achieves a minimum and a maximum on a compact set. Okay. So if you're minimizing a continuous function on a compact set, you always have a minimum. So existence is quite simple if the set is compact. If the problem is, and remember here I always need non-empty because without non-empty nothing happens, right? So non-empty. Notice I haven't said that the function, so in this case when I moved back and forth, I haven't said that this function is convex. So remember, I start with these functions as convex. I reach a VI, so I need convexity of these functions. But this VI, when I observe that it's the stationary point of some other optimization problem, that optimization problem could be non-convex. Okay, now what happens if X is closed but not bounded? Not bounded, which means not compact. F is continuous. So then you need, then F needs to be coercive. What is coercive? Let me define it. Coercive, loosely speaking, means if you go in any direction and go infinitely far away, the function goes to plus infinity. So just think about a situation where the function is nice in a bounded set and you don't want to hear. I can't imagine why he doesn't find this interesting. Anyway, so coercivity just means that this is equal to infinity. Okay, this is a coercivity condition. Now, let me give you an example of functions which are coercive, functions which are not. Okay. So if I gave you this function, I think in my exam just now I gave a function to remember what I gave. So let me just start with a simple one, okay? So this one, this I mean this is kind of obvious, but what is this? Is this function coercive? Right? So the way we establish that is we notice that this is x1 minus x2 the whole squared if x1 goes to plus infinity and x2 stays constant, this goes to plus infinity. If x2 goes to plus infinity, f goes to infinity. Okay, and if both x1 and x2 go to plus infinity, right, you still have that this happens, right? Now, there is one case where I have to be careful. So the one case I have to be careful actually about this, because if x1 is equal to x2 and they go at the same rate, then this is not coercive. So I need an extra term here. I need 2x1 squared, 2x2 squared. So I get x1 squared plus x2 squared. So the reason why I do this, why do I add this, is because suppose I send x1 to infinity and x2 to infinity, and I set x1 directly equal to x2. Now what happens to this function if I didn't have this?
Zero.
It's just 0. Right? So sometimes things look coercive, they're not.
But the infinity minus infinity is
So no, but then what happens is that when you're looking at this, you're not going to, so you don't want to take it to the limit and then subtract. You never do that. What you do is you say, along the way this is 0, so nothing is changing. For every iterate, they're equal. So it's basically like a sequence of zeros. Okay? You don't want to take it to the limit and subtract. That's not valid. Okay? You never want to get into the infinity minus infinity operations. Yes?
I last track somewhere. There you tried that minimization problem over x1 and x2,
Uh-huh.
the one on the left top.
Yeah.
To those two problems on the right.
On the right. So what I did was, I said this problem, this is the gradient of this problem. The gradient of this problem can be viewed as a map f. Now each of these is the gradient of a different problem. And so what you can see is that if you look at the variational conditions of this, they're exactly vi x R2 gradient of little f, where this is f.
But the problem on the bottom left, we could not express it.
Yeah, in this case, so now, so what you had was you had an integrable game, so this is equivalent to that. When you have a non-integrable game, this is a non-integrable game. If you write this, you cannot construct such an f.
So I mean, in more complicated cases, how can we like?
So you can't use this avenue. So this avenue is only when the Jacobian of the mapping is symmetric. If it's not symmetric, you cannot use this avenue. Then you have to go back to this avenue. Okay, so there are two avenues: integrability, non-integrability. This was a case where integrability was satisfied, so you can use optimization avenues to analyze compute equilibria. There are settings when it's not satisfied, and then you have to use techniques associated with variational inequalities directly. Yes?
When you say, so to be sure, when you speak about existence, like existence in non-integrability, you speak of the existence of this
Equilibrium, yeah.
That's right, okay. And here you say it's a mini, so when there is integrability,
Yes.
non-convexity, as it is in that case.
Yeah, so the non-convexity here doesn't affect you because all you need is stationarity, right? So if a problem is non-convex, so if I'm minimizing a problem like this, suppose I gave you a non-convex problem, right? What does the variational inequality represent? It represents, the solution of the variational inequality represents stationary points. Now, if you've got a non-convex function, you can, your solutions will capture any of these stationary points. Okay? But as far as you're concerned, it doesn't matter. And the reason why it doesn't matter is because these stationary points represent the stable points of that game. Right? Because what is that stable point? Because remember, when you have non-convexity, that non-convexity comes from these interactions. right? Because if you don't have these interactions, assuming that this is nice, you have convexity. Now, if this is also not nice, then that would show up here as well. That's okay, that can happen. Like for instance, if I had a situation where this was negative half x squared, it doesn't matter. It will just be negative x squared here, right? But it just means I have a non-convex game, right? And then computing equilibria might be harder. If I want to directly claim existence, it's harder. But if you told me that the set is compact, I now know that the equilibrium corresponds to the stationary point of an optimization problem. If it's coercive, I can use these ideas. So it's, there are lots of kind of turns and twists. And so the hope is I can give you enough so that you can at least navigate most of them, right? Now, okay, so there was this question here about coercivity. So coercivity is, what about uniqueness? Yeah, so yeah, Vladimir.
Follow up on this symmetry, just to come back to this later. Does the integrability principle hold for Q-symmetric matrices?
Skew symmetric. So when you have a skew symmetric matrix, so that's why it's skew symmetric, you have to be a little careful. So what I want to tell you about skew symmetric matrices is the following. So suppose I told you that f of x lambda was something like this. Gradient of f, let me just say some. Let's make it constant for the time being. Okay, let's make it constant. Ax minus b transpose lambda bx. Now if I take the Jacobian of this, I get A minus B transpose B 0. Now what you notice is this is equivalent to minimizing half x transpose AX subject to Bx non-negative, where lambda is the multiplier. Okay. Now, the reason why yesterday, Anubhav, I talked about this is that you could, when you write it out, put a minus b here. Right, and well, you could, yeah, because it's if it were an equality constraint, you could just put a minus b here. And if you did that, you might say it's symmetric, right? And then you try to solve it. In that case, so I know what I'm trying to remember what I said yesterday, it got late. So, so you clearly can't do it when it's an inequality constraint. If it's an equality constraint, if you did that, you clearly recover the KKT conditions, but if you then try to minimize it, the question is, that, okay, you're getting a stationary point, and from the standpoint of it being a stationary point, maybe it suffices. So I think maybe it will. So for instance, if you did this, so suppose, so a question was raised yesterday after the class with, let me come back to that, okay? I want to just come back to this part because I feel like this is a different direction. Let me go through the existence and uniqueness for the integrability, and then I'll come back to that because it'll. So this was existence. If you wanted uniqueness, if f is strictly convex, so this is uniqueness, and a solution exists, this implies it's unique. Okay, that's a simple setting. Strongly convex, then a solution exists and is unique. Okay, if f is strongly convex,
Uday, let me give you an example. we have two generators.
Mm-hmm.
Both their costs are quadratic,
Mm-hmm.
so it's strictly convex.
Mm-hmm.
But they have exactly the same cost function.
Mm-hmm.
So it means that our allocation, production allocation with the two generators, and the
No, there's a single allocation. If they're both convex, strongly convex,
both strongly convex, but exactly the same cost function.
exactly the same.
Two generators of
So you take C of x1 squared plus C of x2 squared. So, but they have to be quadratic,
yeah.
right? So you've got this. This has a unique solution.
If they have a linear term as well, if they have linear cost component.
No, so for instance, if I wrote this out, plus dx1 plus dx2, if you take the first order conditions, what do you get?
x1 plus x2 is equal to something.
So you get, so no, if you differentiate this in x1, you get 2c x1 plus d. So it has to be a minus is equal to 0. 2c x2 minus d is equal to 0. So x1 is equal to d upon 2c. x2 is equal to d upon 2c. Right? I think the point you're trying to make is that suppose you changed it, you don't change cost. So suppose you change x1 by epsilon, but if you changed x1 by epsilon, the thing is that if you're doing that, then why do you have two different cost functions? I mean, it should be just, if they're independent generators, then there's some sort of,
I guess when
what
cost functions are the same, any arrangement of
should be this, with the same output.
the demand, I mean, that works. So it's not unique.
No. So wait. Let's be careful about this. So the thing is, what you're telling me is that if x1, now look at this problem. So in this particular case, you have so in this particular case, if you have x1 plus x2 is equal to d upon c. D upon c, right? Yeah, d upon c. So what you're saying is that suppose I made x1, so as long as I meet this constraint, both of them have the same cost, right? But now look, once you set this constraint, then you're solving a different optimization problem. So you have to be very careful about, so if you solve this optimization problem now, let's see, x1 squared. So I'm trying to see whether, so this clearly has a unique solution in terms of x1 and x2, but what you're saying is that you can get the same cost with other solutions.
Yeah, with the constraint x1 plus x2 is equal to 10. Something.
No, because it's quadratic, then, no, it's like 1 plus 1 equals 2, but
No, but from,
half and half, then the cost would be more.
so is that, if with the quadratic, is that true actually? Because, so if I had 1 plus epsilon, so suppose I took this and I reduced this, I don't know if that's true. I don't think it's true to change it, because look, if I changed x1 to d upon c plus epsilon, and I change this to d upon c minus epsilon, sorry, d upon 2c. Now what's going to happen is you're going to get, the cost of this is going to be c1 squared, and this is going to be c1 squared minus d c1 upon 2c plus epsilon, c1 upon 2c minus epsilon. So this epsilon will cancel, but I don't think these epsilons cancel. I don't think so. So I don't think it's true. Anupar, you had made this point, but I don't think it's true. If we have quadratic costs, you can't, it's not fungible. You can't move between this. It's true for the linear case, but if it's quadratic, a small increase here increases the cost significantly. So I don't think, because look, if you change this by epsilon, this cancels, but this one doesn't. Okay, so I was like suddenly wondering, did I make a mistake? But no, it's right. It's only a unique solution. Right, there's a unique solution. Okay. So today in the morning, I just wanted to make sure, because I felt like I was moving at a pace which wasn't commensurate with what what we needed to achieve. I just felt like I was. So we want to make sure that we're all on the same page. So I don't mind spending more time on this just to make sure that we all understand. There's a lot here, right? But I want to make sure that we all understand. So just again. Yeah, sorry.
It's not this question. This last one you just showed now. So
Yeah.
what is the brackets beside D? Why is it different? Where did that come from?
Oh, the reason, so the question that was asked was, suppose you have two generators with cost C1 x squared minus dx1, cx2 squared minus dx2. The question was that when you write down the optimality conditions, you get a unique solution. So the question was, you've got two generators with the same cost. Suppose I just change the allocation to make sure that they still have the same overall, should the cost be the same. But it's easy to see. So that is true actually if it's linear cost. If the cost was linear, if you increased one and decreased the other, you'd get the same cost. But because it's linear, you don't have strong convexity, so you don't have uniqueness. But when it's quadratic, if you changed generator 1's cost by epsilon, this is the new cost, the quadratic part. This is the new linear part. This is the new linear part of x2, and this is the new quadratic part, this is the new linear part. These two cancel, but you can see this plus this is not the same. So this is not the same as C1 d upon 2c the whole square times 2. Okay. So, yes.
Just to check if
Yeah.
I understood the problem. If we add an inequality constraint or inequality constraint, that means that in the Nash equilibrium we will have other players with dual variables, or not? I mean, if I add an equality problem, an equality constraint to that problem,
Yeah.
in the Nash equilibrium equivalent Nash game, I have another player.
No, that's not true. So what is, so remember when you're looking at this entire set of relationships, we look at the sets as if they're just algebraic sets. So don't any kind of constraint structure within it, we've not dealt with. It's like the engine in a car, you just keep it inside, don't look at it. Okay, because all you're doing is, you're using the objective to assess what is the associated VI. Is that clear? Yeah, Olivia.
That was the case with the skew symmetric.
Yeah.
I was curious whether it's possible, like, for example, if the original game is where two people are competing, one is maximizer and another is minimizer.
So when you have so I can write down the skew symmetric. Once I'm done with this, I'll make sure that I go through skew symmetric. But I want to make sure that we all agree, because now I'm going to build on this in the slides. But I want to make sure that we all understand the roadmap. Gwen, is that clear? Okay. Where did I start? Oh, here it is. Jonathan, what's your name in the back? I forgot. Yeah. No, Stefan. Yeah. Is it clear? Okay. So I start just a last round and then we'll move to the slides. Okay. I have a Nash game. I need convexity of the theta i's. Need convexity of theta i's xi, sorry, to show an equivalence between the variation inequality x comma f. Okay. In this variation inequality, the map is the concatenated gradient map. The set is a Cartesian product of the strategy sets. Okay. Once I have the variational inequality, there are two avenues. One is I notice that the variational inequality is actually now, so we have to be careful. The VI implies, so the minimization of this problem gives you a VI for any so even if you had you need a differentiable function, but you don't need convexity. Okay. So now if you want, from that standpoint, it suffices for you to examine this object. Examining this object, requires you to say, okay, if I have now just, all the equilibria that I'm concerned with are stationary points of this problem. So I can check and see if a stationary point exists just from Weierstrass's theorem. In fact, Weierstrass's theorem allows you to say when a minimizer exists. We know a minimizer is a stationary point, so we actually are able to say a lot more. And this is both in the case where f is continuous, and x is either compact or just closed and not bounded. Uniqueness, you need f to be strictly convex or strongly convex. Okay. Second step, suppose you find that the mapping is not integrable. Now remember, the integrability notion is important. When you write down the game, this is an example of integrability. You write down the game, you write down the gradients of the objective, and you write down these. If you take the Jacobian of that, so you take the second derivatives, if you find it's not symmetric, if it's symmetric, then you know it's an integrable game. Okay? It's not always true, as I showed here, that the Jacobian is symmetric. Look at this game. This game leads to a mapping whose Jacobian is not symmetric, so it's not an integrable game. You can't use the integrability avenue. If you cannot use the integrability avenue, then you need to use the standard VI approach, and we've provided conditions for which existence can be claimed in that approach. F is continuous, X is closed, convex, non-empty, compact, gives you existence. Or here's another coercivity condition. There are other conditions. Okay. Now you might say, how do you apply these conditions? Well, you need to analyze your game. If you analyze your game, you need to actually, and we'll do that in some cases here. Okay. And what about uniqueness? If the map is a strictly monotone map on X, then you immediately have uniqueness, assuming you have existence to begin with. And you also have it under a different condition when F is a P map, which I'll define later. Okay. Questions? Yes. Yeah. No. Good.
So, on the integrability case,
yeah.
We say that f is coming from basically from the Jacobian of f.
Wait, you mean little f or big f?
The small f is coming from the Jacobian.
Yeah. The small f is the Hess is yeah. So the Hessian of f, little f, can be viewed as the Jacobian of the big f.
Big f, exactly. So then, is there any case when f is continuous but not differentiable? Because I guess we are.
Yeah, I mean, you could have a situation. So the thing is that when it's so here we're going to work with differentiability, because if it's continuous, then what happens is that when you write down the VI actually the mapping is set valued. So you could still have this, but then it would be the optimality conditions of a non-smooth convex problem, for instance, and that basically requires you to use set valued maps. So I don't want to get into that here. Anything else? Yes, Anu?
I'm not sure. I don't know if it's true for that case or not. Maybe this is a quadratic function that has a saddle point
a saddle point? A what point?
As the stationary point.
Yeah, stationary point, yes.
It's a saddle point and not a minimizer. In that case, we would not look for a minimum, but just for a stationary point.
So the thing is that the issue is that once you, so remember, we don't start from here, right? We usually start from here, right? Once you start from here and you reach there, then all you need is a stationary point of that to get an equilibrium of this, right? So that's important to know, that so that it does make things a little easier.
So in case we don't have in case the big f is integrable,
Yeah.
and that the resulting function, let's call it the potential function,
Yeah. It's not a potential function.
No.
I know. So that whole avenue of potentiality I'll talk about if I get time. But it's actually a very rich approach as well. But again, it's not that easy to get potential functions. But you're right, it's some function, yeah.
Let's call it it's not convex.
Yeah.
So we may have a minimum, we may not have a minimum. In case we don't have a minimum, we just look for
So you have to be careful. So the thing is that it may be that there are functions for which the stationary points, like I have a function in the in the slides you'll see, I think it's minimizing e raised to minus x on the non-negative real line, right? That is basically the solution is at infinity, right? If you minimize e raised to minus x, so if you minimize this function, right? The stationary point, I mean, it's actually a minimizer, which is also a stationary point, that occurs at infinity, right? So now the thing is that whether you get stationary points with finite norm, I don't know, I mean, it depends on, but assuming you can get one, then yes, that stationary point is an equilibrium. Because the stationary point gives you exactly the VI, gives you the variational inequality problem. Okay?
Okay, just to be sure that I understand well. What I understand is that in some case, the function is integrable, and the integrated function won't be a convex function.
Yeah.
In some cases, we can write it like this as a minimization problem. In some cases, when the minimizer does not exist, we can't write it as an optimization problem.
No, wait. So you can't write as optimum only if it's not integrable. It could be that. Yeah. No. So think about it like this case. So in this case, suppose I gave you this game. This is the mapping. If I take the Jacobian, it's this. This cannot be written as an optimization problem, right? So no optimization. Now you could have an optimization problem whose stationary point is at infinity, but that, so I could write a game, get a game. Turns out the equilibria are given my solution to this problem, but this problem, the solutions are at plus infinity. So but that you can't help. It just means the equilibria are unbounded.
Yeah. I mean, the function little f.
Yeah.
Is it always bounded from V?
No, not necessarily. There's no way I can.
In that case, we don't write it as a.
No, but you could write it, but it just means that it may not give you. You might get stationary points which are, in some sense, the equilibria are at, unbounded. I mean, you get some equilibria at plus infinity. So it's in some sense a game which is a little, unstructured. Right? There's nothing that I can guarantee that tells you that the solutions of these are bounded. It could be, because look, using this you can construct a game whose function is this. And what do you do with this? It's just one of these peculiar settings that come up. Christy, your question?
I think it's just something silly. I'll just come up there.
Yeah.
Now they are substituting x1
Yeah.
into the equation, but I just saw c1 over 2c. I was wondering where the c1 came from.
Oh, there's no C1, there's just C, it's just from here. When I write down the first order conditions, it's a convex optimization problem. The first order conditions are 2C x1 minus d equals 0, 2C x2 minus d equals 0. x1 is d upon 2C, d upon 2C. And the question that was asked was, look, they have the same cost, quadratic and linear. Can you increase x1 slightly and reduce x2 and get the same overall allocation? Does that lead to the same cost? That's only true if there is no d. If there is a d, what happens is if you change one of them by a small amount epsilon, and this is the new cost, and you reduce the x2 by a small amount epsilon. Why am I doing that? Because I want to make sure their total amount is still d upon c. That's the optimal, right? D upon 2c plus d upon 2c is d upon c. So the question was, suppose I make x1 a little larger and make x2 a little smaller, but make sure that their summation is still d upon c. Does the overall cost stay the same? And the answer is no. You can just check it. So the reason, so this was just to kind of make sure that this works with the theoretical understanding. In theory, there's a unique solution. Intuitively, it seems like I can construct a second solution or multiple solutions. But no, the answer is there is still a unique solution.
But the question in the bracket beside d is supposed to be, that's supposed to be x1.
Which,
So it is actually.
what?
It should be d over c1 should be d there.
Oh, no, wait, D, oh, right, I'm sorry. Yeah, I apologize, that's a typo.
I've seen that there since.
Huh?
I've seen that there since one.
Oh, okay, I'm sorry about that, yeah. Okay, so then, So, oh, we take a break? Okay. Yeah, okay. It's a good time to take a break. So if you guys want to take a picture of, because what I want to do is I might erase a small portion to talk about, so I want to first go through the existence results for a more general problem now. Because now you understand the pathway. Now we're going to add a little more machinery. Once I've added the machinery, I'll come back to some of these special cases like not the saddle point, the skew symmetric case.